Better? Yes. All right then. All right. So I think I've got my work cut out for me because some people knew at least STARTTLS, but nobody thought it was insecure. So let's see how you think about this at the end of this talk. All right. All right. Let's start by taking a quick look at the email ecosystem. So let's assume we have a sender, Alice, that wants to send an email to Bob. Both of them use a so-called mail user agent, or in short, a MUA, or what you would normally call a mail client, like, for example, Thunderbird. Both also have a so-called mail service provider, for example, Gmail, or in short, an MSP. Now Alice wants to get their email to Bob. First, they will have to talk to the mail submission agent, or the MSA. So just an SMTP server, for example. In this case, they will have to configure. Does this work? Not really. All right, then. Whatever. They will have to configure a host, a port, and an encryption mechanism. In this case, STARTTLS. Then that will get the mail to the SMTP server, and Bob on the other side will have to do the same for the mail delivery agent, so just an IMAP or POP3 server in this case. Then the mail reaches Bob, and that is basically the connections we will be focusing on during this talk. But I don't want to leave you hanging, so how does the mail get from there to there? We have the mail transfer agents, or short MTAs, of both MSPs talking to each other some way over the internet via SMTP. And this is generally considered to be a pretty hazardous field, so certificate validation is hard, DNS is hard, so that's why we are not talking about this, because it's generally assumed to be at least somewhat insecure. So we will be talking about the first and the last hop, so submission SMTP and IMAP and POP3. However, at least in our opinion, the first and the last hops are the most critical ones, because in these steps, user credentials are transmitted. So just a single insecure connection gives full access to the victim's mailbox, with all catastrophic consequences you might imagine from that. We therefore define our attacker model as follows. We assume an active meddler in the middle that can manipulate TCP packets in plain text, but not break TLS in any way. So no actual TLS attacks here. So let me now give you an introduction to STARTTLS, starting with a little history lesson. The email protocols SMTP, POP3, and IMAP were all defined before SSL and TLS were really a thing. Therefore, they were, of course, plain text only. And there were plain text ports defined for these protocols in the first place. Note here that the standards distinguish between transmitting mail from MTA to MTA and submitting a mail to the MSA. So there are two ports defined for that. With the advent of SSL and TLS, ports were defined for implicit TLS, so just speaking the protocol over TLS, so what you would normally see for HTTPS, just for POP3, IMAP, and SMTP. And there were new ports for that. However, it was considered to be wasteful to have two ports for the same protocol. So in 1998 and 1999, the STARTTLS mechanism was defined to allow for what is called opportunistic encryption. So basically, the mail server and the mail client will negotiate TLS if they both support it. To this day, Wikipedia's STARTTLS article redirects to the opportunistic TLS article, so that kind of gives an idea how people think about STARTTLS nowadays still. And we, on the other hand, think that there's absolutely no reason for STARTTLS to be opportunistic in mail clients nowadays, because your mail server should really support TLS by now. So when adding STARTTLS, the implicit TLS port for SMTP was revoked by the ANA, since they realized the mail ecosystem, and especially MX records, do not allow for specifying ports. Sadly, they also removed the port for submission, for no apparent reason. But since 2018, it's all good. There was RFC 8314, which is aptly titled Clear Text Considered Obsolete. The implicit TLS ports are back, and they are now the ports you should be using for email. And we even got an implicit TLS port for submission back. SMTP, MTA to MTA is still a mess, though. But it's being worked on by people. So let's look at STARTTLS at the example of SMTP. Upon connecting, the server sends a greeting telling that they are smtp.example.org. Alice's Moore will respond with an elo command, to which the server responds with their capabilities. In this case, just STARTTLS. The client sends a STARTTLS command, to which the server responds that I will do this now. Everything up until this point was basically in plain text. Now client and server will perform the actual TLS handshake, and everything after it will be encrypted. The client will again ask for capabilities, to which the server responds that they now support authentication. Alice's Moore will authenticate and send the actual email. But next, let's talk about what STARTTLS stripping means. Assume again that we have this active meddler in the middle that can manipulate TCP packets. Therefore, they can simply strip the STARTTLS capability from the elo response, without the server or the client realizing, because nothing is authenticated here. Assuming that the client is really opportunistic, they will first not send the STARTTLS command, second, not perform the handshake, and third, send everything in plain text. This is, of course, pretty problematic because Alice's user credentials and their email will now be transmitted in plain text, with the attacker still listening. Of course, the server could potentially block any commands except the STARTTLS command, but nothing would prevent the meddler in the middle from hijacking the whole now unauthenticated and unencrypted connection and pose as a legit mail server to the mail client. But it, of course, does not stop here. What if the attacker changes something over here, like pretending the STARTTLS command failed? Or over here, like adding an insecure extension to the elo response that Alice might use later on? Or here, like adding some data after the STARTTLS response before the handshake that might be interpreted like anywhere. It turns out that when you start digging into the details, you will find that exceptionally many issues in real-world applications exist with STARTTLS. And of course, it does not stop with SMTP. This is an IMAP trace. The concept is basically the same. It starts with a greeting, they negotiate STARTTLS, they perform the handshake, but what happens if an attacker changes something here, or here, or here, or here, or here, or really anywhere? All right, let's slow down a bit and take a look at the research. During our talk, we will consider 4 questions regarding STARTTLS. First, we wanted to find out if modern clients are still opportunistic in their use of STARTTLS, and will fall back to plain text if it's not available. If that would be the case, an attacker could simply use one of the well-known STARTTLS stripping attacks, like the one I've shown you before, to force a client to send sensitive data in plain text. In that case, there would really not much to be learned here. So let's assume for now that that is not the case. So second, we analyzed what potentially sensitive data is exchanged in plain text and how clients might be coerced into exposing additional sensitive data in plain text. Third, we looked at what data is retained from the plain text phase after the transition to TLS. So nothing is authenticated before the TLS handshake, and really no data should spill into the encrypted phase, of course, as well. So finally, we looked at what happens in error cases. So all protocols have some kind of error mechanism, and we wanted to know what happens if these errors happen before the TLS handshake. So an active meddler in the middle could force errors to happen or just inject errors. And we wanted to know what clients do with these. All of this accumulated in a Usenix Security 2021 paper called Why TLS is Better Without STARTTLS, on which Damian will now give you the details.
Okay, thanks, Fabian. So, as Fabian has motivated, STARTTLS leaves really a lot of room for mistakes, but let's step back for a moment and explain our methodology. What we wanted to do is to obtain a very broad view on the STARTTLS ecosystem, meaning that we wanted to test as many clients and as many servers as possible, possibly coming from different platforms such as Linux, Windows, and Mac, but also from mobile platforms such as Android and iOS. And especially in the mobile space, we have a very interesting platform that is called CloudMail. And in CloudMail, what a mobile application is doing is that it does not talk with the email server directly, but instead it instructs a third party to do the email communication for it, for example, via HTTP. So for example, if any one of you is using Outlook or MyMail on Android, your password is basically first transmitted to this third-party backend, which will then do the email communication for you. However, this means that we cannot really observe what the system under test is doing, which is why we have, right from the beginning, restricted our tests to network-only black box testing, which means that we need to have a test set or a set of test cases. What's also interesting here is that generally it is a lot easier to test email servers than it is to test clients, because typically an email server will constantly listen for new incoming connections. In clients, we had here to get a little bit more creative by using pre-configured snapshots and virtual machines such that we could basically request connections, so to say. And now, how do we create a good STARTTLS test corpus? What we did was, in the first place, we conducted a literature review. In this review, we queried CVE databases, bug trackers, and search engines for keywords such as STLS and STARTTLS. And what's interesting here is that already at this stage, we could create a small test corpus, and as we will see, that 2 of the most devastating attacks were already present at this time. And basically, we just had to apply a well-known issue to a new set of email applications. And the second thing that we did was to conduct a protocol analysis by taking the protocol specifications into account and thinking about how we can generalize the found problems. As a result, we ended up with a test corpus containing more than 100 STARTTLS specific test cases that we classified into 5 distinct attack classes. And for the remainder of my part of this talk, I will go with you through each of these classes and explain the most interesting findings that we found. So let's start with the negotiation class. In this class, the aim of the attacker is always to derail the STARTTLS connection such that TLS is not made in the first place. And the two most prominent, or the most prominent example of this is STARTTLS stripping, as Fabian showed in the introduction. So an attacker can here strip the STARTTLS or remove the STARTTLS capability from the server response, make the client think that STARTTLS is not supported, which means that the client will not do or not participate in a TLS handshake. And besides changing the message flow a bit, the result is that the attacker can obtain the password in clear text. There is a second variant of STARTTLS, which consists of changing the response code of the STARTTLS command, but basically the result is the same as for this first variant. And now I think there is an even more interesting case, and this is called the pre-auth greeting, or the pre-auth attack. And here we already changed the greeting type itself by exchanging the OK response with a pre-auth response. And now it is not clear what happens in this case, and to understand it, we need to look at the IMAP state machine. And if you look here, you will note that IMAP defines multiple types of greetings that transition the client to different states. So, for example, the OK greeting will transition the client into the not authenticated state. However, when you use the pre-auth greeting, the client is expected to directly transition into the authenticated state. This can make sense, for example, if you're using IMAP via an already authenticated connection, for example, SSH. But now something interesting happens. IMAP is pretty specific about which commands are allowed in which stage, or in which state, and the STARTTLS command is not allowed in the authenticated state. This means that the client would basically violate the specification should it do the STARTTLS command. But the alternative is clearly to do something similar as to STARTTLS stripping by not doing the STARTTLS transition at all. But here there's something more we have to consider. Because as I explained to you, the client is now in the authenticated state. So you can ask yourself, why should it log in again? And in fact, if you have a standard conforming client, it will not do the login, but maybe proceed with the select command instead to select the inbox. And now the question is, what does it gives us as an attacker? What we could do here is to, for example, mimic a valid IMAP server and, for example, present an inbox that is almost empty but only contains a single message asking for ransom, for example. But we can do better. If the client supports the mailbox referrals extension, we as an attacker can instruct the client to select the inbox on another server, for example. And this should remind you a bit about the HTTP redirects. And because the attacker can choose the domain name freely, they can use a name that they have full control to, or where they can obtain a valid TLS certificate to. So this means that at this point, the attacker can just do the full handshake, including the transition to TLS, but still obtain the credentials from the login or from the network traces. So in total, we found that 15 of the tested applications were vulnerable to certain forms of negotiation attacks, but we have to be a little bit careful here. Not in all cases we could obtain valid user credentials, but at least in every one of these cases we could obtain sensitive data such as sent emails or drafted emails. Which brings us to session fixation attacks. As I have explained, the STARTTLS command is not allowed in the authenticated state, and it turns out that there is a very good reason for that. Consider our user Alice, who wants to communicate via implicit TLS, meaning no STARTTLS involved at all, with an IMAP server. So this means that both parties are in a state where the next thing that is expected is the TLS handshake. And now also consider our attacker. What they can do is, in the first step, to first get a hold on the connection. And then, instead of proxying Alice's connection directly to the IMAP server, the attacker would connect to the server, receive the greeting, log in with his with their own account, and then initiate the STARTTLS command afterwards. And now it should be evident that what the attacker could do is they can just exchange the port number of Alice's connection and start to proxy the TLS data directly to the IMAP server and vice versa. And this means that when Alice tries to log into the server with valid credentials, she will unexpectedly receive a login that tells her that she is already logged in as the attacker, which is unsettling, at least, I think. We found that we can exploit two email clients with session fixations to obtain user credentials. But in 9 additional cases, we saw at least fragments of session fixations with not so clear impact for security, or at least where we could come up with a working exploit. And the next class is tampering. The aim of tampering attacks is always to try to make persistent changes to the mailbox of our victim. For example, by already telling before the STARTTLS command was already sent that there is a new email in the inbox. Or, for example, by telling that a new folder was created. And in fact, if you do this in Thunderbird, for example, you will see that now there is an attacker-controlled folder in your email client, which will not go away. In total, 5 of the 28 tested email applications do accept IMAP responses even before STARTTLS was conducted, also with varying consequences, but we know of at least one client where we could, for example, delete the whole mailbox by doing things like that. Which brings us to UI spoofing, which is similar to tampering, but in UI spoofing we are not interested on the permanent part, but instead we want to show dialogues to our user, for example, for effective social engineering attacks. And here IMAP helps us a bit because in IMAP there is a dedicated response that should be showed to the user. It is called the alert response. And when you do this, when you execute this trace, for example, in Outlook, you will receive something like that, which looks pretty much like a benign email, but with the additional information that this message was sent with high importance and a large or a attacker-controlled field that you can, for example, use for social engineering attacks. In total, considering the alert response code and also different error mechanisms, we were able to present a user attacker-controlled dialogues in 11 of the 28 tested clients. And now let's come to the buffering class, which is, I think in our opinion, the most interesting class of attacks in STARTTLS. And here we have to get into a little bit more detail about protocol handling itself, or in other words, where is the data buffered to, where is it passed, and so on. So let's consider now that we are a server. And as a server, our first task is to send a positive greeting, which means basically that we are able to, or that we are willing to accept new commands from a client. And then the client will send us something. This something is first read into an internal buffer. And then the next step is that this buffer is parsed, and the server detects that it's indeed the STARTTLS command and removes it from the buffer. Then it responds with an OK command. Now both parties are in a state where TLS should be made, and the TLS handshake is executed. Then Alice sends, again, something that is buffered, parsed. The server detects that it's indeed the login command, maybe even with valid credentials, and it responds with a positive response, meaning that Alice is now authenticated. But let's consider buffering or the command injection case. Again, let's assume that we first sent a greeting, and then a client sends the STARTTLS command. But now, instead of just stopping at this point, the client will also additionally, in the same TCP segment, add additional data. For example, this one here. So in fact, this data is, again, buffered first, and then the server tries to pass what it received. So it will detect the STARTTLS command, remove it from the buffer, and respond with an OK command, which means the STARTTLS is now, that STARTTLS should be executed. Then both parties execute the TLS handshake, and Alice can send her new command. But what should be now, I think, pretty evident is that this data is appended to the internal buffer, which means that when the server parses this buffer, it will not detect the recent command, but in fact the command that was sent even before TLS was made, meaning that it will get an invalid command. And now the effect is that even though Alice has the right credentials, she will receive a command telling her that she sent, for some reason, an invalid command. So I think how you should think about this problem is that the command we sent up at the bottom, the invalid command, is interpreted as if would have been sent via an encrypted channel. And basically, both parties do not align on the meaning of the session, which leads to pretty interesting attack classes. And besides that, credential stealing is almost always possible in the protocols. I think the most adventurous attack we could come up with is by hosting valid HTTPS content through an IMAP server. So let's consider that case. Again, we assume that there is a user Alice. And she will do implicit TLS, no STARTTLS involved at all, to communicate with an HTTPS server now. And we also assume that inside of this structure, there is also an IMAP server that shares the same TLS certificate with the IMAP server, or with the HTTPS server. And now we also have our attacker, which first gets a hold of the connection. And then, instead of directly proxying Alice's connection to the IMAP server, the attacker will first prime the IMAP server towards a certain state by using the command injection. It will receive the greeting, then send the STARTTLS command, and then send a very specifically crafted set of valid IMAP commands that somehow resemble artifacts of HTTP. So the server will respond with an OK and expect the TLS handshake. And now at this place, the attacker can just proxy Alice's connection to the IMAP server. And now what happens so this is an instance of cross-protocol attacks, and what happens normally in cross-protocol attacks is that you get somehow a result, but the impact is often not so clear. So in this case, what would happen is that Alice sends an HTTP GET command to an IMAP server, which is obviously something you should not do and leads to likely some error cases. But because we have primed the server towards a certain state, we can control the output of the server, meaning that the output it will generate reassembles something that looks very, very close to valid HTTP. And although I know that some of you might note that there are some syntax elements missing, at least recent browsers such as Firefox and Chrome will accept this response and show a valid HTTPS website without any certificate problems at all. In total, we found 8 new instances of command injections in our test. But what's even more interesting about this case is that it was already described more than 10 years before by Wietse Venema, the author of Postfix, in 2011. And when we take all these issues into account, so the historic issues we know that servers were vulnerable to the command injection, we see that in total 16 of the 23 email servers were vulnerable to command injections. And I think this should point you to the fact that these are not merely implementation issues, but really an issue with the specification itself. We can generalize this attack also to a response injection, which mimics the same kind of buffering injections as on the server side to the client side. And also what we see here is that 16 of the 28 applications are vulnerable to command injections. Okay, so let's continue with internet scanning.
Right. Yes, this works again. All right, Damian gave you an overview of all the issues in mail servers and mail clients. However, we found it especially interesting that we still found servers vulnerable to the command injection 10 years after it was first published. Therefore, we took to internet scanning to learn how widespread these issues are still in practice. Of course, scanning always comes with a lot of things you should consider. Of course, we applied standard best practices. We used a block list to prevent scanning people who do not want to be scanned. We handled a lot of abuse mails, asking for us to put people on the block list. We identified ourselves during our scans, for example, using the elo command or using comments where possible, so people could actually contact us and know who we are. And finally, we published a website stating what we are doing on the scanner IP address, so people could look it up and again get the abuse contact. However, we realized that this just does not cut it for email scanning. So due to spam problems, mail transfer agents especially will not talk to everyone. There are mail-specific block lists that are hard to get out of. Therefore, we need an untainted IP for scanning. So our normal IP address we used for scanning was basically on all the email block lists that you could imagine. And there really was nobody who wanted to get us off that. So we decided to take a new IP address first. Then we realized MTA still won't talk to us because, well, they expect you to be an MTA as well. So you have to run an SMTP server on your scanning IP address. Then you need to publish appropriate DNS records like an MX record and a pointer record, and SPF and DKIM records help if you are new to email sending, which a mail scanner server usually is, because we will not be sending any emails over the server. So people would want you to have these records as well. And finally, we were made aware of an email-specific allow list that might have helped in getting the mail server over the threshold of being accepted by other servers as well. But that is pretty hard to measure, really. All right. Our main question while scanning was, how many servers are still vulnerable to the command injection that was first published in 2011? Surprisingly, out of the 60 million servers we could scan, 2% were still vulnerable to this bug. Interestingly, this percentage is higher for IMAP and POP3. From our disclosure, we know that most server developers were aware of this bug in SMTP, but not really in IMAP and POP3, possibly because the original bug came to be known as the STARTTLS SMTP bug, but not for the other protocols. So we've talked a lot about issues, now let's talk about fixing them. The most straightforward thing to do as a mail user is to switch to implicit TLS. So that's a pretty easy fix for all the issues in mail clients. Server providers, on the other hand, should also evaluate if they can cut StarTLS support in the future, for example, by migrating existing users that still use StarTLS to TLS in some way. However, recognize if you have a large user base, this might not be a workable solution for everyone. Therefore, if you really must use StarTLS, you should isolate the plaintext phase completely from the TLS phase by clearing any remaining state after it. This includes clearing any application buffers, hopefully also fixing the buffering issues in the process. And finally, as both an implementation and a standardization measure, we recommend streamlining the StarTLS negotiation, only sending and accepting the bare minimum of messages before transitioning to actual TLS. So no complex negotiation, no actual other extensions, just a StarTLS command and the handshake. Finally, I want to tell you about interesting things we learned from our disclosure. We included this part in our talk because reviewers and readers kept asking about this, and we think there's something to be learned here. Just to remind you, there were a lot of issues uncovered in clients, servers, and on the internet. Of course, this means a lot of disclosure, and disclosure is never easy. So this issue Damian posted on GitHub, on a GitHub repository of an open source mail library, is pretty representative for disclosure. I'd like to report a security vulnerability, but I don't know how. Let's start with some lessons we learned during our disclosure. First, to answer one of the questions we asked ourselves in the beginning. Clients are not meant to be opportunistic. Most of the developers we talked to recognize the issues as vulnerabilities and fix them. So STARTTLS, at least in mail clients, is not opportunistic. As said before, server developers knew the command injection SMTP, but not in IMAP and POP3, which kind of surprised us. And the last lesson ties back to the issue Damian posted. Contacting developers and admins is still hard nowadays. If we could just all agree to use a security TXT or have some way of letting researchers know where to contact people, that would be really great. All right, this ties back to the last point, and let's talk about disclosure of scan results. Communicating scan results can be especially hard because it's hard to get a hold of the affected admins. You usually just have an IP address and no real mail address to contact, and even if you can contact the admins, what do you tell them? You cannot always tell which server they are actually using. We tried identifying servers, but that doesn't work that well. And patches are not always available. So what do you tell them? And this is where the German BSI cert came into play. They handled all the communications with the server admins in Germany and helped us contact national certs so that they could contact server admins in their countries. So special thank you there. While scanning and reporting to the bigger mail service providers, we had some interesting experiences. One of them paid a bounty, but never fixed the issue. One silently fixed all issues and stopped answering to our emails. One argued that STARTTLS is really meant to be opportunistic and there was nothing to be done, even though we presented a real vulnerability to them that could be kind of bad. And some never responded or had really no way to contact them that would get us past the normal customer support. So that ties back to adding a security TXT, please. All right, of course, while scanning, people contact you as well, which is a nice change of pace from the normal disclosure. Asking what you are doing, asking you to stop, and so on, and so on. Turns out that people seem to be monitoring their mail servers especially well. Most of these emails are automated, of course, and this is just an excerpt of the emails we got, but we had some interesting conversations, to say the least, with real people. However, this is not where the fun emails stopped. We reported an issue to an open source mail client that commonly appears on top 10 lists of most used email clients. Yeah, turns out their bug tracker is overrun by bots trying to sell us watches, like lots of bots selling lots of watches. And we never got a hold of the actual developers, and we think this client might be unmaintained. We also had an interesting experience while disclosing to an open source client. We found an older issue requesting TLS to be enabled by default, which seemed quite sensible to us. However, the dev responded that they tried this in a previous release, but it resulted in an issue about a configuration being broken by a user. Therefore, this change was reverted in a later version. We decided to take a closer look at this broken configuration issue, and we realized that this was a mail user that was in fact attacked with STARTTLS stripping. So in this case, the STARTTLS command never reaches the server because it is X'd out somewhere in between the STARTTLS command and it reaching the server. So of course, this would cause breakage when the client enforces TLS. But let's end these tales on a more positive note. Of course, we had lots of positive experiences, so this is non-exhaustive. For example, most open source developers were a pleasure to deal with. Also, of the big MSPs, 1&1 Mail Media GmbH, known for GMX and Web.de in Germany, really stood out, answering fast and detailing what they're doing throughout the whole process. So that was a nice change of pace as well, in contrast to the other MSPs I've told you before. But the open source projects are really where it's at. It took the MUD developer all of 55 minutes to release a patch for us to test. The Trajita dev took a day, and explained to us why the issue happened in their code in the first place and requested a CVE themselves. And the Thunderbird developers were especially helpful, doing a lot of research themselves and giving us now new ideas to improve upon our own research and improve the paper. So let's tie this all up. In conclusion, we found that compared to implicit TLS, STARTTLS adds attack surface to email protocols without adding anything of value, really. Furthermore, we found that STARTTLS implementation in both servers and clients have widespread issues hinting at systemic problems with STARTTLS. As we have shown, the effect of this vulnerability is not limited to STARTTLS, but also allows for cross-protocol attacks, for example, against HTTPS and implicit TLS versions of these protocols. We conclude that TLS is better without STARTTLS, and STARTTLS should be avoided where possible. And for all of you, we recommend looking into your own email client to check if you're still using STARTTLS for some old mail account. And if you find to do, consider changing that and talk to us about it at the social event tonight. And now we're happy to take your questions.
Okay.